Hi, this is the second part of the walkthrough of the Edexcel A-level Chemistry Specimen paper, paper 1. First half is in an earlier video. As with specimen papers, the questions can be a bit different sometimes. They don't want to use their best questions up on specimen papers, and sometimes the wording isn't as clear as it could be that you would get in a real paper. And there's a few instances of that. Also, I say that if you're finding this paper difficult, it is a lot harder, considerably harder than all the other real papers that have been. The real papers are not as difficult as this. Okay. Right. Sodium can form 3 oxides. Okay. It's been suggested. Okay, so there's the 3 oxides: the oxide, the peroxide, and the superoxide. So you can tell from the formula of them, because sodium is always a 1+ ion, that the oxide is the O2- ion, the peroxide ion is O2- and the superoxide ion is O2-1-. And you probably never heard of the superoxide ion before. Suggested that superoxide could be used in spacecraft to regenerate oxygen. Oxygen needs to be replaced because the astronaut oxidizes glucose, so that's fairly familiar. Superoxide, and we can regenerate oxygen by this equation. So it reacts, so it's doing 2 things here. It's using up the carbon dioxide that the astronauts have breathed out, and it's making new oxygen. But the key to this, if you notice, is that it's not using up as much carbon dioxide as it needs to, right? Because every time the astronaut makes 1 mole of CO2, he uses up 1 mole of oxygen. Well, here you're making 3 moles of oxygen, but you're only using up 2 moles of carbon dioxide, and that's why they need to use this one, the normal oxide, to absorb the carbon dioxide that is not absorbed as a result of generating the oxygen in this equation. Okay, so that is pretty difficult to digest all of that, right? Especially the way the question is worded, right? So what we've got to do is calculate the mass of sodium oxide here that would be required to remove the excess carbon dioxide when exactly 880 grams of sodium superoxide are reacted per day. You can assume that the astronaut oxidizes 2 moles of glucose a day. Now that wouldn't appear in a real paper because you don't need to know that, and that's just confusing. You don't need to know that information. That just sets you off down the wrong track, so ignore that. Right, so what we're going to say is we've got 880 grams of superoxide. Yeah, that is going to make us a certain amount of oxygen and use up not quite enough carbon dioxide, so then we need a bit of extra of this to use up the extra carbon dioxide. Right, so how are we going to go about that then? Right, okay, so let's find out the moles of superoxide then. Superoxide used up, so that's mass over mR, which is 880, and the mR is 55, which works out to be exactly 16 moles. Okay, now, so now we're going to say, we're going to look at this equation here. "16 moles of superoxide." Well, that is going to promate, that will make, so 4 moles of superoxide make 3 of oxygen. So 60 moles of superoxide will make 16 multiplied by 3/4. There's the 3, there's the 4, 3/4 moles of oxygen. And that is equal to 12 moles of oxygen. Right, now let's see how much carbon dioxide is used up by the superoxide. So CO2 used up. by the superoxide? Well, if we look at the equation, 4 moles of superoxide uses up 2 moles of CO2. In other words, 1 mole of superoxide uses 0.5 moles CO2. We had 16 moles of superoxide, so 16 is going to use up 8 moles of CO2. But let's see, when that means, right, when we generate 12 moles of oxygen, we need to be using up 12 moles of CO2. We're not using up 12 moles, we're only using up 8 moles. So moles of CO2 left over is 12 minus 8, which is 4 moles. And that's got to be dealt with by the sodium oxide. Okay, so this equation shows us 1 mole of sodium oxide uses up 1 mole of CO2. We need to use up 4 moles, so we need 4 moles of sodium oxide. Now it says we want the mass of sodium oxide, so it's just moles times mR. So the mass of sodium oxide, we're running out of space a bit here. Let's do it in red. Mass of sodium oxide is equal to moles times mR. 4 times the mR of that is 60, of sodium oxide is 62. So that's equal to 248 grams. Right, so that was a very difficult question, I think. I don't think the wording is quite clear enough to lead you down the right path. And also this business here of putting this irrelevant information about the moles of glucose the astronaut is using up each day is just likely to put you down the wrong path. So I don't really think that question would appear in its current form in a real paper. Okay, right. Dot cross diagram to explain why the superoxide is a radical. Well, they're telling us there that we've got a single bond between the 2 oxygens. So let's draw a dot cross diagram. Oxygen is in group 6, of course, so 6 electrons in each an outer shell. Right, let's do this oxygens as dots and this one as crosses. So we're going to have a dot and a cross, a single bond there. This one, you're going to have 5 more electrons. Now, because it's negative, you've got an extra electron, which is taken from somewhere else. Do that one as an X. So that oxygen's all right. It's got a full outer shell. This oxygen has only got 5 electrons left. So you can see it has only got 7 in its outer shell, and it's got this electron is unpaired. So it's a free radical. It's more difficult than your average dot cross diagram, I think. Okay. Right, sodium peroxide reacted with water. Okay, the hydrogen peroxide produced let's have a look at that then. So was determined by titration with a solution containing cerium ions. In this reaction, the hydrogen peroxide is converted to oxygen. Okay, so what we need to start off with, this is pretty unfamiliar, but let's see, we've got here, it tells us the concentration and the moles of the cerium 4+ solution. So let's work out the moles of cerium. Conc times volume, that is equal to 0.42 multiplied by 24.85 over 1,000. That is equal to 0.010437. Now, what we want to try and do is we want to find out what the ratio of the cerium reacting with the hydrogen peroxide is. That's what we need to find out here. Okay, so can we find out the moles of hydrogen peroxide? Right, let's do that then. The hydrogen peroxide and titration. Well, the hydrogen peroxide all comes from the sodium peroxide. So let's work out the moles of sodium hydroxide. Sodium peroxide, we can do that because we've got the mass. Moles, sodium peroxide. So, sorry, wrong formula. Sodium peroxide, Na2O2. That's equal to mass over mR, which is 0.403 divided by the mR of sodium peroxide is 78. That's equal to 0.00516. Now let's look at the equation. It shows us here 1 mole of that of sodium peroxide gives us 1 mole of hydrogen peroxide. So the moles of hydrogen peroxide there, therefore, are moles H2O2. It's the same as that. Sorry, yeah, 0.00516. Right, so we've got a ratio now of the cerium to the ratio of Ce4 plus to the hydrogen peroxide. That is 0.0104 to 0.00516. And I think you can see, without using a calculator, just divide by the smallest number, that is a 2-to-1 ratio. Okay, I'm going to clear a bit of space here now. Right, so the cerium and the hydrogen peroxide react in a 2-to-1 ratio. You need 2 moles of cerium, 4 plus for every 1 mole of hydrogen peroxide. Well, let's look. The hydrogen peroxide here is losing 2 electrons. Loses 2E minus. So that means the cerium, because you need twice of it, each mole of cerium isn't losing 2, it's only losing 1 electron, because you need twice the moles of cerium and hydrogen peroxide. So that means cerium 4 plus is going to lose an electron plus E minus. So what have we got there? We've got cerium. It's got to be cerium 3 plus ion. Okay, so that is the formula of the cerium ion. So you have to work out basically the ratio of them losing electrons and gaining electrons in this redox reaction. Get them, and do that from the number of moles reacting, and then you find that. Okay, another hard question, I think. Right. Tidy up this. Right, equilibrium now. The following reversible reaction is used in industry to make methanol. Okay, so carbon monoxide plus hydrogen goes to methanol, and it's exothermic. That's probably going to be useful later on to remember that, which would affect both the value of the equilibrium constant and the proportion of methanol. Now it's a bit of a giveaway. The only thing that affects the value of Kc is the temperature. Nothing else affects it. It will affect the position, but not Kc, and that's a common trick question they ask. So you just have to home in on that one straight away. It's B. Right. A lot of people think, well, how come, if you increase, let's see, it says here, increase the pressure. Yeah, well, that's going to make the reaction, it will make the reaction move to the right. But it will not affect the value of Kc. And the reason why it won't do that, if you increase the pressure, you've got to decrease the volume. It's not asking you why, but that is why. So you're changing the volume. So, and those two things cancel each other out, and the effect of Kc, it doesn't change at all. Okay, so Only temperature affects the value of Kc and Kp, if you ever get that question. Right, expression for the equilibrium constant is given by that. Right, so I've drawn this little table out ready. Okay, so the usual thing we do is write down the equation and then I write down start moles, used up moles, and the equilibrium moles. So let's fill in this table. And then right now it's asking us to find Kc. So the pressure, you don't really need to worry about that. It's not asking you to find out Kp, so that's kind of a bit irrelevant. Right, so we start off with 0.2 of carbon monoxide, 0.4 of hydrogen, and no methanol. At equilibrium, we find there is 0.086 of methanol. Okay, 0.086 of methanol. So let's see there then. Right, so that means we must have used up 0.086 of carbon monoxide. So how much we got left? 0.2 minus 0.086, that's equal to 0.114. Right, if we've used up 1.86 of that, we've used up the double the amount of hydrogen. So the amount of hydrogen is 2 times 0.086, which is equal to 0.172. So the amount of hydrogen left over, 0.4 minus 0.172, that gives you 0.228. So we've now got the equilibrium moles. Now we need to think about putting them into this expression, but we don't put moles into that expression. Square brackets mean concentration, so we need to work out the concentrations. And they tell us the volume is 1.2. So don't forget conc is equal to moles over vol, dm cubed. So I'm going to do equilibrium conc here. That's 0.14 over 1.2. That over 0.12, sorry, 1.2, and that over 1.2. Put the numbers into the calculator, you find you get there. All right, so this is equal to 0.095. This is 0.19, and this is 0.0716. So put those numbers into the equilibrium expression, and we need to, okay, so Kc is the methanol concentration over the carbon monoxide concentration multiplied by the hydrogen concentration squared. So that's going to be 0.0716 divided by 0.095 multiplied by 0.19 squared. That is equal to 20.89. Now, number of significant figures, all the data was given to 3 significant figures. I put here, they said that many moles, 0.200, so that's 3 sig figs, 0.04, and so on. So we should give this to 3 sig figs. So that, now the units, what have we got? Well, we've got, we're going to have mole per decimeter cubed on the top, divided by mole per decimeter cubed to the power of 3 on the bottom. So that's equal to 1 over mole squared dm to the minus 6, which is mole to the minus 2 dm to the plus 6. Okay, that's the units. Okay, that was a fairly standard sort of question, but usually what they do is, because in a normal paper they get you to do this table here, and then they don't get you to work out Kc with those values, because if you've done that wrong, then you're going to get the wrong answer. So they usually say in another experiment you had this, and then so they break it up into 2 bits. They don't usually run through with the whole calculation, I think, because it's too hard for them to mark when they get like error carried forward if you make a mistake in the first bit. Okay, next bit. Now we need to remember that this is exothermic for this question here. Right, it says the equilibrium mixture. Okay, so let's just write down the equation again, just to show. We've got CO plus 2H2 goes to CH3 OH. And they're all gases, okay? And this was delta H was negative, it said earlier on in the question. So it said if the equilibrium is heated in a sealed container to a higher temperature, since the gas volume remains the same, the increased temperature results in an increase in pressure. Explain why it would be difficult to predict the effect on the yield of that. Okay, so you've got two things working against each other. Increase the temperature. This is an exothermic reaction, so it will move the equilibrium to the left. So you get less methanol. But when you increase the temperature, you're also going to increase the pressure, which will, you've got fewer gas moles on the right than the left, so that will move equilibrium to the right. So you've got more methanol at equilibrium. So you've got two factors working against each other, so it's pretty hard to predict what the final effect is there. That's what you've got to say for that one, I think. Okay, on to acids and bases, equilibria. Okay, so mixture of sulfuric and nitric acid is using the nitration of benzene. The following equilibrium is set up. Okay, now what's statement about this? What's true about this? Now you probably know, but look what's happened to this. This has gained a proton. And this, so that means that the nitric acid has behaved as a base. Concentrated nitric acid behaving as a base. This loses a proton, so this behaves as an acid. So, right, is this true? Nitric acid, and are these a conjugate acid-base pair? Yes, they are. Definition of a conjugate acid-base pair: two species can be interchanged by addition or removal of a single proton. And that's who they are. The nitric acid is not acting as an acid, acting as a base. No oxidation or reduction occurs. All the oxidation numbers stay the same there, so C is wrong. And that's wrong as well. Okay, so let's move on. A bit of space here. All right, okay. Sulfuric acid ionizes in two stages. Explain with reference why the equations why this is a weak acid. Right, so with the equations, they've given a normal arrow for that one, so that's not an equilibrium reaction. That goes to completion, so that is a strong acid. But they've given an equilibrium sign here, so that means that it's reversible and it doesn't completely dissociate. So HSO4 minus is a weak acid. It doesn't completely dissociate or completely ionize. Okay, so now I think following on from that, 0.1 molar sodium hydroxide, sorry, 0.1 sulfuric acid has got a pH of 0.97. Okay, calculate the concentration of hydrogen ions in the solution. So pH is equal to minus log to the base 10 of that H plus ion concentration. So that means H plus is equal to 10 to the power of minus pH. 10 to the power of minus 0.97 gives us a value of 0.107 mole per decimeter cubed. And incidentally, they don't ask you this, but incidentally, you can see that the sulfuric acid hasn't completely ionized, because if you've got 0.1 mole of sulfuric acid and it completely ionized to that, the concentration of hydrogen ions would be equal to 0.2, and it's not as high as that. So you can see the second ionization is a weak acid. Right, now we have got a fairly straightforward buffer calculation. There's nothing unusual about this one. Okay, so we need to, whenever we're doing a buffer calculation, it's a good idea to write down the expression for Ka. A minus, where HA is the weak strong acid and A minus is its conjugate base, and then rearrange that to give us H plus concentration is equal to Ka multiplied by concentration of HA over A minus. So the hydrogen ion concentration of a buffer, and hence the pH, is always dependent on two things: the Ka value, which doesn't change, and then the ratio of the concentrations of the weak acid and the weak base you've got in the mixture. Okay, but it's good to rearrange that equation like that. Okay, so let's work out now. Now we can't put the concentration of HA. Look, it tells us the concentration of ethanoic acid 0.5 because it gets diluted because you mix it up with something else. So there's a couple of different ways of doing this. So the way I like to do this is, let's work out the moles of HA. It's the concentration times the volume. Well, the concentration was 0.5 multiplied by the volume, 400 centimeters, that's 0.4 dm cubed. So that's equal to 0.2 moles. Right, now the final concentration of HA is equal to moles over the volume. I'm not going to bother working out the total volume, the concentration, because I'm just going to call it V, and we'll see it cancels out. So that's going to be 0.2 over V. Now let's do for the moles of the HA, of the A minus, sorry. Moles of A minus, sodium salt. Okay, concentration times volume again. The concentration with 200 centimeters cubed of 0.5 mole per decimeter cubed sodium ethanoate. Okay, so concentration is 0.5 multiplied by 0.2. That's equal to 0.1 moles. Okay, again, I'm going to do the so we don't put the number of moles into this equation here, do we? We put the concentration. So I need to say the concentration of A minus is equal to moles over volume is equal to 0.1 over V. Now those V's are going to cancel out, that one there and that one there, because it's the same volume, because they're both in the same mixture, aren't they? So let's put the numbers in. H plus is Ka 1.74 times 10 to the minus 5 multiplied by, right, HA is 0.2 over V divided by 0.1 over V. The V's are going to go. We've got 0.2 over 0.1, which is actually 2, isn't it? So work out 8. So we've got to do H plus is equal to 2. So let's do it that way, more logical. 1.74 times 10 to the minus 5. This thing becomes 2. That's equal to 3.48 times 10 to the minus 5 moles per decimeter cubed. Take the minus log of that to give us the pH, and we get pH is equal to 4.46. That's to 2 decimal places. Okay, so that's a pretty straightforward buffer calculation. Complex ions now. Okay, Prussian blue is a dark pigment used in painting and dyeing. Okay, Prussian blue is formed when an iron 3 salt is added to a solution containing the complex FeCN6,4-. Okay, the cyanide ion has the formula Cn-. What's the oxidation number of Fe and FeCN4- ion? As I make that a little bit bigger, I think. Okay, well, we've got a charge of 4- there. We've got 6 cyanides, each of which has got a 1-, so that's -6. So that means the Fe must be +2. +2 minus 6 gives you -4. So that is the oxidation number of the Fe. Draw a diagram to show the shape of the ion using the structure Cn to represent the cyanide ligand, and show how the cyanide ligands bond to the central ion. Right, it's 6 ligands, so it's going to be octahedral. So I would draw Fe. These ones are going back into the plane of the paper. These ones are coming out. That they're all in a square. This is a square planar, this bit here. And then we've got one ligand sticking up and one ligand sticking down. Now show CN minus and show how the cyanide ligand bonds to the central white. Well, the way the cyanide ligand bonds is, and I haven't really explained that very clearly what they want you to do. Well, we've got negative charge, but it's the lone pair on the carbon which forms a dative bond to the central ion. So you just put CN, CN, CN. Do that way around so that you can, it's definitely the carbon which is forming the dative bond. Okay, that's what I draw for that. Right, a solution containing Fe. Right, so who make this a bit bigger. Okay, a solution containing this ion can be made from this ion in 2 steps shown. Name the type of reaction taking place in steps 1 and 2. Well, let's have a look at step 1. We can see here that all we've done is we've replaced these cyanide ligands, these water ligands, with 6 cyanide ligands. So this is ligand exchange. Just there's no oxidation or reduction occurring there. The ion here is obviously got to be Fe2+, and in the previous question we worked out it's Fe2+ there, so there's no redox occurring there. Now let's look at step 2. This isn't ligand exchange. Straight away, probably the easiest way of seeing this is, look, the chlorine has got an oxidation number of 0 there, it's the element, but here it's -1. So the chlorine has become reduced. So straight away we can say it's a redox reaction. There's redox going on there. Incidentally, the chlorine's being reduced, something else is being oxidized. And if you look, it's the ion, because here it's a +2 oxidation state. And here we've got 3-, then 6-, so there must be 3+ there. So the ion has been oxidized by the chlorine. It's a redox reaction. Right, this is a fairly straightforward recall of your knowledge question. A separate reaction, aqueous sodium hydroxide was added to a solution containing iron 2 sulfate. A green precipitate was formed that turned brown and standing in air. Identify the green precipitate. Well, you start off with FeH2O 6 2+, that complex. Now when you add OH- to it, it will remove protons and remove 2 of them, and it forms the uncharged complex. That uncharged is always insoluble, and that is a green precipitate. Now, the oxidation number of the ion in there is obviously +2, but if you leave it in air, air contains O2, which is a pretty good oxidizing agent, and it oxidizes the ion 2 to ion 3, so you end up with this precipitate. So you need 3 hydroxides to make it uncharged this time, because it's a 3+, and that is the brown precipitate. And question 10. Okay, so about the thermal, explain the trend in thermal stability of the carbonates in group 3. Right, you have to know that as you go down group 2, sorry, as you go down group 2, the carbonates become more stable, sorry. MgCO3, calcium carbonate, strontium carbonate, barium carbonate. You have to heat them to a higher temperature to make them decompose. Now, why they're more stable? Well, it's due to the size of the positive ion, the cation. Okay, magnesium ion is 2+ and small. By the time you get to barium, it's much bigger. So there's lower charge. Well, let's say this way around. Higher charge density here, and that polarizes the polarizing the carbonate ion. Which makes it easier to decompose into carbon dioxide. So this is the magnesium ion has got a higher charge density because it's smaller and polarizes the carbonate ion more. Okay, right, on to this question, which is about this is about enthalpy of solution, calculating enthalpy of solution. Okay, so magnesium chloride is soluble in water. The enthalpy level diagram is shown here. Okay, so what we've got here is when you dissolve the gaseous ions, okay, that's okay, into, sorry, get the gaseous ions and form the solid ionic thing. So that's the lattice enthalpy, minus 2493. Here we're getting the gaseous ions and we're putting them into aqueous solution. So we're going to hydrate them. So you're hydrating one magnesium ion, so that's going to be minus 1920 kilojoules per mole, and two chloride ions, so that's minus 364. So we add that lot up there, we get 2,648. Okay, and that is going down, so that would be minus. We don't really need to worry about that. So we want to find out this bit here. We have just got to subtract. We'll do 2,648 minus 2,493. That gives us 155. And we need to think, what is the sign? Is it negative or positive? Well, the arrow is going down. It's exothermic, so it's a minus sign. So that is the enthalpy of solution, 155 kilojoules per mole. Okay, now this is a badly worded question, or not very clearly worded. So the table shows some data relating to dissolving magnesium sulfate. Okay, so delta H of solution is exothermic, negative, and the enthalpy of the delta S is that. Explain why dissolving magnesium sulfate in water is exothermic by considering the enthalpy changes involved. Well, I first looked at this question and I thought, well, it's exothermic because it's minus. What more do you need to say? I think what they want you to say is, right, you've got to think about when you dissolve magnesium sulfate, what you've got to do is you've got to break up the lattice to form magnesium ions and sulfate ions. And that is obviously very endothermic, a big positive value. And then also you're going to hydrate these gaseous ions into aqueous ions, and that, because you're forming those lots of interactions with the water molecules, that's very exothermic. Okay, so now because this is negative overall, this must be more negative than this is positive. Okay, so in other words, you get more energy out from the hydration of the ions than you have to put in from breaking up the lattice. Okay, and that's not very clear from the wording of the question. That they want that. Okay, use the data in the table to calculate delta G when magnesium sulfate dissolves at 298 Kelvin. So we need our equation there. Delta G is equal to delta H minus T delta S of the system. So delta G is equal to, now we have to be careful, this is in joules, not in kilojoules, so we need to divide it by 1,000. So we're going to have minus 87 minus 298 multiplied by minus 0.210. So that's minus 87. 298 times 0.21 minus 62.58. Right, so that's going to be equal to plus, isn't it? Okay, so delta G is equal to minus 24. Kilojoules per mole, 24.4 kilojoules per mole. That tells us, because it's negative, minus, it is feasible. The reaction is feasible. So that means magnesium sulfate should dissolve in water at 298 Kelvin. Okay, table 2 shows some data relating to dissolving barium sulfate. Okay, so and calcium sulfate. This is the last question on the paper, I think. Right, 6 marks. Okay, so comment on the relative solubility of the barium sulfate and calcium sulfate. So we need to work out delta G for both of those. Okay, so we do it the same way as before. Right, delta G is equal to delta H minus T delta S. So let's do it for barium. Delta G is equal to, right, we've got plus 19, and then we've got minus, now they've converted this into kilojoules for us, we don't need to divide, minus 31, which is plus 31, so that's going to be 19 plus 31 is equal to 50 plus 50 kilojoules per mole. So that's barium sulfate shouldn't be soluble then, because delta G is positive, and so it won't be very soluble. Let's do it for calcium. Same calculation again. So we've got minus 18 this time, minus 43. So it's still positive. It's going to be plus 25. Okay. Now, you need to say that because, right, the barium one is a lot more positive. So it's going to be a lot less soluble. You might expect the calcium sulfate to be slightly more soluble because of that. Okay, you probably don't need to, but you might want to write delta G is equal to minus RT ln K, the equilibrium constant. Now, dissolving both of these things is going to be in equilibrium, so let's think about this. Calcium sulfate going to calcium, right? It's an equilibrium. So okay, but how much of it dissolves? Well, if you've got a very, you can see here, if delta G is negative, then K will be a large positive value, and that means that it will, you're going to have you're going to have a lot of calcium ions and sulfate ions compared to the in solution. Okay, if delta G is positive, the opposite is true. K is going to be small, and the more positive delta G is, the smaller K is going to be. So that means you're going to get less ions in solution at equilibrium. Okay, I think I'll leave that is the end of the paper.